All right, last time, guys, I introduced you to graphing with transformations, and we talked about how we can graph anything with a transformation if we know the parent functions and we know the transformations. We focused on absolute values since that's the unit we're in, so we're going to keep going with some absolute values, work a little bit with the transformations from equations and verbal instead of just from the graph. So this first part here wants a verbal description of the transformations compared to its absolute value parent function. And so the parent function, remember, is y equals the absolute value of x. So these two absolute value bars tell us that's what we want to start with, is the absolute value parent function. But we've got four different transformations here. And so when it asks for a verbal description, you want to talk about each one of these parts and what it does to our graph. And so I'm going to start with the negative up in the front. This here is in the place of the A. And so we said when A is negative, it causes a reflection across the x-axis. So the negative on the outside of the operation is a reflection across the x-axis. When you write that, make sure you write across the x-axis because there's reflections across the y and other reflections. So you do have to be specific with that. Reflection across x-axis. All right, for the number now, we look at this number, and if the value is bigger than 1, it's a vertical stretch. If it is between 0 and 1, it's a vertical compression. So 2/3 is between 0 and 1. So this is a vertical compression by 2/3. So our scale factor is 2/3. Now with absolute values, remember that works just like the slope. So instead of going up one and to the right one, we would go up 2 and to the right 3. This would be our rise. This would be our run. Since it is negative, then we would actually go down 2 and to the right 3 to get this graphed. All right, our next one here is in the place of C. So this part was in the place of A. This is in the place of C. And so when it is x minus 3, we say it goes to the right 3 units. The C value there would be 3 because remember the minus is part of the formula. So C is 3, and so we're going to the right 3 units. And then our last one is the D value. It is outside of the absolute value bars. So everything on the outside of the absolute value bars is going to affect the Y values. Everything on the inside is going to affect the X values. And so this goes up 8. All right, for the second example here, before I can get started giving my transformations, I need to go ahead and make sure this is in the transformational form. And this is not. When we talked about transformational form, we said nothing can go in front of the x. It needs to be factored out. So my first step is going to be to factor that 2 out. And when we factor, what we're doing is undoing the distribution. So 2 times x gives me 2x. And 2 times 2 gives me that 4 right there. So I have now factored out what was in front of the x, which is the b value. This is the transformational form. You can't start from this one because you would say something like left 4, and it's not. It's left 2 here. So make sure it's in that transformational form first. All right, so this would be down 5. And then this part right here is our b value. And so we said everything inside of the operation affects our x values. So that is our horizontal. And so we said if b is bigger than 1, which in this case it is, it's 2, it is a horizontal compression by, and the scale factor is 1 over this b value, so it would be by 1/2. A horizontal compression looks very similar to a vertical stretch. So keep that in mind when you're dealing with these Algebra 2 functions. All right, the next thing we're going to do is we're going to go from verbal to equation on this one. It tells us that we want to write an equation in general form for the graph of the absolute value parent function. So they're telling us that so we know which operation to start with. We're going to start with that one there. And so it says shifted 6 units down and 2 units to the right, vertically stretched by a scale factor of 3 and reflected over the x-axis. So the first thing I want to start with is y equals. It told me to write an equation. So if you're missing an equal sign, you haven't written an equation. So make sure that's your first step. And then we're going to put in our operation, which is the absolute values. Now we start working on our transformations. It says shifted 6 units down. So that's the D value. So 6 units down would tell me to do a -6 in the place of the D. Then it says 2 units to the right. So we know that's inside. Outside affects the Y, inside affects the X. So 2 units to the right, that would be a horizontal one. So we would do X minus 2 is my shift to the right. The next part, vertically stretched by a scale factor of 3. So we know that this right here is the A value. And so 3 goes on the outside. Vertically, that affects my Y value, so that's going to be outside of the operation. And then reflected across the x-axis is when we have a negative on the outside. So now we've written the equation that has those transformations. We're going to shift over to this second one here. But I'm going to go ahead and change this vertically because I don't like there's not an example of horizontal. So I'm going to change this to horizontally on our notes here so that we can practice one of those as well. All right, so it says shifted 3 units up, 2 units to the left, horizontally compressed by 1/2, and reflected over the y-axis. So I start with my y equals, and I put my operation there. All right, so 3 units up, that's a +3. 2 units to the left, that's when we're on the inside and we do an x plus 2. This is left 2. It's supposed to be x minus, and so since it went to the left, that gives me a -2, and the minus negative cancel out to become a plus. All right, horizontally compressed by 1/2. Well, remember when it was horizontally compressed by 1/2 right here? In the equation, it was a 2. We had to flip this to get the scale factor. Well, now they're giving us the scale factor, so we need to flip it back to put it in our equation. So this would be a 2 right here. All right, and then reflected over the y-axis, that's a negative on the inside. So the reflection across the x is a negative on the outside, a reflection across the y is a negative on the inside. So there's our equation. All right, for our last one here, again, I always start with whatever the parent function is. And so now we start on our transformations. If you want to go ahead and pause and then come back and check your work to make sure that you can write one. All right, so shifted 4 units down, that's going to be a -4 here. Vertically compressed by a scale factor of 1/4, that's the A value, it's on the outside of the operation. Reflected across the x, that's a negative, and then to the left one is an x plus 1 on the inside. So that's how you write the equation given the verbal descriptions. You're going to work backwards to figure out is that A, B, C, or D and put it in its place. All right, now let's look at a graph and writing the equations. So we said if you know the transformations, you know the parent functions, you can graph anything without a calculator. Well, the same works for working backwards. If you know your parent functions and you know your transformations, you're able to write an equation. So in both of these cases here, we have an absolute value. So I know that my equation is going to be y equals, and it's going to have the absolute value bars. I can tell because that's what the parent function looks like for an absolute value. Now, when we were graphing these, we talked about C and D is the vertex. So our vertex is C comma D. So that's the first point I'm going to want to find on this graph right here. It went to the left 2 and down 4. So this is -2, -4. So here is my vertex. That's my C value, that's my D value. And so we know that on the inside, it's x minus the C value, which is -2. So that's going to turn into a +2 there. So x plus 2. That's the left 2 from our parent function that starts right there. We're here. Now we went down 4 to get a D value of -4. So we're going to have the -4 there. The last piece you have to get is the A value. Some people are really good at seeing it from the graph. So we're going to do it a couple ways. We're going to look at it from the graph, and I'm also going to show you how to do it algebraically so that for sure you know how to do it. All right, so right here with the absolute value, we're pretty lucky because it works like the slope. And so it went up one to the right one, up one to the right one, and it keeps going. So our slope is 1. That tells me there is no a value here. Well, the a value is 1. We did not have a stretch, we did not have a compression, and it's still facing up, so we have no reflection either. So we are done with our equation there. Let's try this one now. So first thing I'm going to do is my y equals and have my absolute value bars. I find my vertex so I can get that c and d value. So this went to the right 3 and up 2. So the vertex is at 3, 2. We said this is c, this is d. So inside my equation here, I know it's going to be x minus the c value, which is 3. So x minus 3, which went to the right 3. And then my d value is 2, so I'm going to go up 2. But we don't know if we have a vertical stretch or compression. This one, we're going to do it both ways again with the graph, and we're going to go ahead and plug in a point so you can see algebraically. So if you can't really see the vertical stretches or compressions on graphs, you can always figure it out algebraically. And so we have written so far on this equation using the vertex, this part. That one's always really easy to see because of the vertex. The a value one is the one that's harder. Now, this graph here has come from this equation. Every single point on this graph comes from the equation. That means I can find any point on this graph and plug it in for x and y so I can solve for a. So right here, I can use this one. Use a whole number one that's easy to plug in. I picked 2, 0 here. 4, 0 would work. You can do 0, -4. So any point on this graph works. So I picked the point 2, 0. So 0 is my y, so I'm going to plug that in. And 2 is my x, so I'm going to plug that in. Now I just solve for the a value. So 2 minus 3 is -1. Now, everything that comes out of these absolute values comes out as a positive. So 2 minus 3 gives me -1. It is going to come out as a positive 1 when it comes out of the absolute value bars. That's what it does. And so we've got 1a plus 2. Now I'm going to subtract this 2 to get it to the other side. So I get -2 is equal to a. There is my a value so that I can write this equation. All right, so that was algebraic. You can do any problem like this to find the a value. Just pick another point on the graph. You already used the vertex, so you don't want to use that one, but any other point on the graph can help you do that. Now let's look at it graphically. The other option you have is we had the vertex 3, 2 to get to this point. We can now look at the slope. And so this went down 1, 2, and to the right 1. And then down, right, down 2 to the right 1, down 2 to the right 1. So there's my slope of -2 because it went down 2 over 1, down 2 over 1. So our slope would be -2. The parent function has a slope of 1. And so since it turned into -2, we know we've got that stretch there. All right, a couple more problems we're going to think through now. These back ones here are really more applying, really thinking through what is happening. So it says, write an equation for the absolute value function that has a vertex of 4, -1, and then the range of -1 to infinity and -infinity to -1. So there's two separate ones here. Now, it doesn't tell you to sketch a picture, but that helps a lot when you're writing these equations and thinking through this. So I'm going to go ahead and sketch a picture. It says the vertex is at 4, -1. So 4, -1, there's my vertex. And it says the range is from -1 to infinity. So it's telling me all of my y values are between -1 and infinity. Well, we know this y value right here is -1. And so if it's going to infinity, that means that this graph has to be opening upward like this. So my equation would be x minus 4 to go to the right 4, and then -1 to go down. Remember, this is c comma d, so that goes right there. I don't need a reflection or a stretch or a compression or anything because this meets the criteria right there, so that would be my equation. Now for this one, again, we're at 4, -1. But here it's saying all my y values are from -infinity to -1. So this would be the highest point on the graph. That tells me that my graph had to have flipped upside down going this way. These y values are coming from negative infinity up to -1. There's nothing above it. So to write the equation, I know I need a negative in order to get it to flip over the x-axis. So I'm going to have a negative there. The rest of this would still be the same because the vertex is still for -1. All right, for our next question, it says determine the maximum and minimum values of f of x equals 2, absolute value of x plus 1 minus 4, on the interval -2 to 3. So this is the entire absolute value, but it's telling us we only care about -2 to 3. So we're going to cut the rest of that graph off. Again, I'm going to sketch a quick picture just so I can see what's happening. So this went to the left one, down 4. It has a vertical stretch, so it's going to be a little skinnier than the parent function, less wide. And so we've got this right here. Now, if we were just talking about this graph right here, the entire thing, it has a minimum value, the vertex right there. But we're not. We're saying we're going to stop this from -2 to 3. So somewhere around here, we're going to lose all of this part, and somewhere over here, we're going to lose this top part. And we're only going to talk about a small portion of the graph. That's what this is doing, is restricting that domain. So we are going to end up with a maximum and a minimum. For the most part, absolute value functions only have one or the other. All right, so our vertex here is -1, -4. We know that because of the CD, again, it went left 1, down 4, so this is -1, -4. Now, I'm going to create a table of values that does this interval right here from -2, 0, 1, 2, and 3. So there's that interval -2 to 3, -2 to 3. All right. We said the vertex is at -1, -4. So that's this point right here. Now we're going to come up with our other values. Well, let's think about this. Here's that -4 is the smallest point right here, and it is going up in both of these directions. Now, we know this controls that vertical stretch of 2. So the parent function goes over 1 and up 1. But because of the vertical stretch of 2, it's going to go over 1, up 2, and then over 1, up 2. So we are going up 2 each time. So this would be -2 on both sides. I went up 2 from the -4. Up 2 on both sides. Then I would go up 2 again, up 2 again, and up 2 again. That would give me all of my y values there for those points. All right, so for our minimum, we already knew that one. That was our vertex right there, -4. Now keep in mind, when it's saying the minimum and maximum value, we're talking about the y value because the value of the function is y. It's the output. And then the max would be the one with the highest number, which is a +4 right there. Let's try that again. If you think you can do it, go ahead and pause this and look and come back and check your work. But we'll do another one. I'm going to sketch this point. So for the vertex on this one, it is 4, -2. So I'm going to go to 4, -2. There it is. This is reflected over the x-axis. So it's down 2. It's facing downward. All right. Now we're going to do our interval. So I'm going to go ahead and make my table of values. In this case, we want all the points between 2 and 7. So 2, 3, 4, 5, 6, and 7. Obviously, there's decimal values as well, but this will give us a good picture here by picking the whole numbers. We said our vertex is at 4, -2. So we are doing this one here. Now we're ready to go. So this one is going downward. It's not going upward. And so we have no vertical stretch or compression, so it's going to do the same amount as the parent function. It's just going to go down. So it would go over 1 and down 1 to get here. So if I go down 1 from -2, that would be at -3. Now, absolute values are symmetrical, so the other side of the vertex is also going to go to -3. And then we would go down from that, which makes it look like this. So this is a max value, our vertex, which again, we can see from here, this was the max right here at our vertex. So we have a max at -2, and then we have a min. Our smallest point on this interval is -5. Now, excuse me. This graph does go down forever, so it would never have an actual minimum. It would only have a maximum, but because of this domain restriction, using only the interval 2 to 7, it does have both a minimum and a maximum value. All right, so there was some more work with absolute values. We'll continue to work with those. Next time we'll be solving